All right, so we are back, and we have here a graphical representation of what we just experienced walking from Mr. McNeil's room, room 206, to the Tardy cart. But of course, since we have to follow the path of the hallways, we didn't actually go straight across because this would send you like flying across the courtyard. But what we did do is we walked 93 steps north, 30 steps northeast, 12 steps south, and 20 steps east, just to recap to get from room 206 to the Tardy cart. And you saw this all previously in the video. So now what we have to know is that each one of these are what's called a vector. And what we have simply done here is combine these vectors on this graphical representation. The first vector we took was to walk 93 steps north. So this is the first vector. It's got a magnitude of 93 steps. Steps being very accurate unit count because my steps are all equal, of course. Yes, very equal. And the direction is north. Now, it's important to know that direction is what differentiates a vector from a scalar. Now, a scalar is simply a measurement of magnitude. For example, saying like 34 degrees Celsius is a scalar. It's magnitude. It's got temperature, but it doesn't have direction, and it would be hard for temperature actually to have direction and to become a vector, because what are you going to say about direction as far as temperature goes? Like it goes up? I don't know. Anyway, so that's an example of a scalar. A scalar could simply be 93 steps north, but by saying that it's 93, a scalar could simply be 93 steps, but by saying that it's 93 steps in the northern direction, then we're giving it direction and thus making it a vector. Now the next vector we went along was 30 steps to the northeast, and then we went 12 steps south, and then we went 30 steps east again to end up at the Tardy cart from our original location, which was McNeil's room 206, the physics room. So now what we have done here on this graph is what's called the head-to-tail method. Now we could simply represent these vectors by drawing them out, by writing them out and saying like 93 north, and 30 northeast, and then 12 south, and then 20 east. But we have actually combined them on a graph, and this is we can imagine this is kind of a grid, or you could just do this with graph paper at home, by actually combining them from head to tail to represent the path that we actually took. So we started with this vector, then we went to this vector, then we went down this vector, and then finally we ended up here. So now it's a head-to-tail method because the tail of the vector is the last part here, but the head is where you put the arrow, and it indicates what direction you're going in. So we've combined the head to the tail of the next vector, and so on until we have eventually got to our destination. So from here, we can very easily calculate. You can kind of graphically show what the representation is. But then if you want to but then the next step, of course, would try and be to find the resultant. And now the resultant is simply the vector that connects where you started to where you end. And this would be, the best path from room 206 to the Tardy cart, which is, of course, just going across the courtyard. But since we can't really fly through windows, it's not feasible. And so we, again, had to follow the path and curvature of the classrooms and the hallways. But if we could, this would be the resultant vector here. All right, resultant. All right. But of course, we can't do that, but it's still useful to know what that resultant might be. Now, of course, this isn't drawn to scale, and it actually gets a little tricky because while we have like 90-degree angles, going north, south, east, that kind of thing, what we do have is kind of like a 45-degree angle here. You call this 45. And so that gets a little tricky, a little confusing, but we'll still go through the math on how to figure that one out. So I'm going to take just a break, and then we'll be right back, and we'll figure this all out.